Hello and welcome back to Let's Code Physics. I have been having some fun working with this rope simulator that we've been taking a look at. I've made another version that I wanted to share with you today that incorporates some surfaces into the problem. So before we saw what happened when the rope could swing from one end, or when it was fixed at both ends, or if it was free at both ends. But another interesting problem is what happens when a rope, like the one we're modeling as a series of springs, hits a surface. So for example, the surface is going to stop some of the atoms from moving, but not the others. And then presumably the others on the surface are going to get dragged after it. This has required a number of additions to the code. The fundamental physics is still the same, but I have had to add some new features. So what I wanted to do today was show you some of the new features that I've added, some of the new conditions that I've had to run through. And then I want to show you just a few of the simple scenarios that I've taken a look at so far, and then we'll talk about where we're going to go next in this series. So the first thing that I've done is because I have these surfaces, so basically they're going to be these red slabs added in. Actually, maybe I can just show you rather than describing it. Basically what we're going to do is we're going to have our rope like we've had before, and we're going to have these red surfaces. This is just a big one at the bottom to sort of catch it. And basically the goal of the code is to keep the rope from going through the surface, which it did there, right? The surface caught the rope for us there at the bottom. Thank you, surface. And in working with these surfaces, I have to be able to tell the code where its edges are, right? So when VPython creates an object, it sets its position as the center of that object and not, like the left corner or the right corner or anything. So I've had to define a few functions, and these actually came out of the FTL beam optimizer code that I've been working with, because there I had to have the left edge, right edge, top edge, bottom edge of each of the rooms in the ship that I'm looking at. In fact, I just copied and pasted this from my latest version of my FTL code, which is why it says room there instead of surface. I could probably change that. I might just leave it there. It doesn't matter what you call it because it's a function. So each of these functions returns the coordinate value of one of the edges. So for example, if you want the left edge of a room, it just takes, or excuse me, of a surface. I'm already thinking of the FTL code. It takes the position of that surface in the x direction, so wherever the center of the thing is in the x direction, minus half of its size in the x direction. So if you're wanting to go to the left, it's starting out of the center, moving half of the thing's width in the x direction, and that puts it at the edge. If you want to get the right edge, it's the exact same function, the exact same calculation, only this minus sign gets turned into a plus sign because then you're moving to the right. And then the same thing for the bottom and top edges. You're taking y minus half the size in the y direction, or y position plus half the size in the y direction. And then same thing for the z direction. For the front edge and for the back edge, you're taking the z position minus half the z size, or the z position plus half the z size to go to the back or to go to the front. And basically that's going to be used later on in the code to evaluate whether the rope or a part of the rope has come into contact with one of those surfaces. There we go. The rope constraints works pretty much the same way as it did last time. I do have a damping coefficient in here just to keep the rope from flailing about wildly. And then down here, I've had to make a number of new lists. So we had the atom list, spring list, and the velocity list before. I've now had to do a force list because I have to update the forces and keep them separated below. But most importantly, I've created these lists regarding the surfaces. So surface list is where all of the actual surfaces are stored, the actual 3D red shapes that the rope will come into contact with. And then all of these front, back, left, right, top, and bottom lists are just the list of the edge locations, so that I don't have to keep calling those those edge functions, which is actually a change I'm going to be making to my FTL code as well, so that I don't have to keep evaluating those things inside the loop every time. I just evaluate them once at the beginning, store them in those lists, and then recall them whenever I need them. Let's see. We're going to start out, as you saw earlier, with the rope horizontal. So this angle, and I should probably make a note of this, is the rope's angle measured from the vertical downward direction. So how about we say from the negative y-axis? There we go. And basically we're going to start it out horizontally. So the setup code is much the same as it was before. I've changed it a little bit to make it so that it's modifying an x and a y, just so that way I can reference those x's and y's later. Those x's and y's later. There we go. Once all the atoms are created, then it creates the surfaces. So we're starting out with just the one surface, the box there at the bottom. I've got its size and location scaled in terms of the length of the rope, just so that way everything is nice and proportional to each other. And of course, these things are going to be red. I've got these two commented out. I'll be adding those back in just a minute. Let's see. And then this is where the code goes through and figures out or stores all of the surface locations. So it takes all of the back surfaces, all the front surfaces, the left, the right, the top, the bottom. So for each surface, it's storing all those edge locations. And then here's our loop. It starts out very much the same like we had before. It's evaluating the spring force, the gravitational force, adding on the previous atom's spring force, and it's now adding on this drag force. And here's where things get both interesting and tedious. So basically, if one of these atoms makes contact with the top of a surface, so if it falls onto one of the surfaces, then it needs to have no force in the y direction, right? Then the surface is going to provide enough normal force to cancel out the force in the y direction. And that's what we're doing here. We're saying that the force in the y direction needs to be 0. And in fact, the force for the previous atom, because the previous atom might be dangling off the edge here, needs to have no y component from the spring force, right? So that way this thing won't swing underneath here and get pulled kind of into the surface, which is not a fun thing. I saw it way too many times until I figured out how I needed to fix it. Actually, I figured out I don't think I need that line for f spring y to equal 0, because I do need the next spring to be able to feel the next atom to be able to spring force, but I'll leave that commented in there just in case. And basically what it does is it checks all of the surfaces for this, because what we have to check is for whether this is for checking whether the atom has come into contact with that surface, and then I have a whole lot of other checks here to see if it's within range of that surface. So for example, I might have an atom that is less than the top. Hello, Pumpkin, so glad to see you. Yes, can you get your butt off the internet, please? Thank you. But in addition to checking that one coordinate, I also have to check whether it's within, the x range and the z range of that surface. So for example, if the surface is right here and the atom is falling this way, there's no reason for it to be caught by that because it's to the right of the right edge of the thing. And that's what I'm checking here. Excuse me. Sorry, I'm mistyping because my kitten's tail is still on the keyboard. And so basically what it's doing there is just checking all of these surfaces. So it's checking for whether this thing is within the sort of the area of that surface. And again, I stole this from my FTL code. It's amazing how these two things overlap. It occurs to me now that I could simply run all this checking within a single loop. Let me think about that for just a second. Hey, that is not yours. I love you, but if you want to be an internet star, you need to do something funny, okay? Okay, cutting back. In fact, I think I can do that. Actually, let me make that change really quick. So I am going to get rid of all these other loops. And so it's only going to check. Yes, it only needs to do one surface loop, because these are not all going to be true, right? It's not going to be in contact with more than one surface at a time. So I can get rid of that, and get rid of that, and get rid of this, get rid of this. All right, frontward and then backward. Okay, so I can get rid. That'll make it run a little bit more efficiently, not terribly more efficiently, but it'll make it run a little bit more efficiently. And then I need to get rid of this. Right, so here I have the while I surface is less than number of surfaces. And so all of these if blocks are taking place within that loop. And I have I surface equals I surface plus 1. And then here we have this part right here. Okay, awesome. Cool. And so basically what I have to do is within each one of these checks, right? So I have 6 possible surfaces for each, 6 possible edges for each surface. I need to call these things something than surfaces because they are three-dimensional. So if each, basically for each face of these surfaces, I need to, run a check for that position there. So here I'm checking for the bottom. Here I'm checking for the left. Here I'm checking for the right. And then I cancel the appropriate force. So if it's on the right side, then there can't be a leftward force. All right, it can't go any farther to the left. So I have to cancel any leftward force. If it's on the left side, then it can't go any farther right, and I need to cancel any rightward force. There we go. And then same thing for the front side and for the back side there. And like I said, the rest is pretty much the same, although I do have to do the same thing with the velocities. So for example, if an atom is resting on a top edge, then it can't have any more negative velocity, so it's got to cancel out a negative velocity there. And I can actually do my same trick here and clean this up a little bit while we tour. So for example here, if it's on the bottom of a surface, then it can't have any more upward velocity. That turned out to be important because at one point the rope, during simulation I was on the rope, curled under and flew back up through the surface, and that was weird. Again, I can get rid of this, and I can get rid of this. Same thing for right and left. If it's on the right side, it can't have any more leftward velocity. If it's on the left side, it can't have any more rightward velocity. Same thing with backwards and the front side. And I do want that I surface equals I surface 1 there. Cool. So the only modifications to I surface are at the beginning and the end. Cool. So I've made my code just a little more efficient in the 10 minutes we've been together. Awesome. Let's see here. Then it updates the position just like before after it's taken care of all of its velocity corrections. And then it just goes through and, updates the spring. So everything else is the same that it was before. All I've done is added in these chunks of checking for the surfaces. And you've already seen it work with the one surface at the bottom. So for example, right now it is falling. It's just in free fall. Well, it does have a drag force, but it's just in free fall until it hits the bottom there, until it hits the surface, the top of this surface. Let's make things a little more interesting here. So that was it, just falling and kind of going flat. Let me show you what happens when this thing comes in when it's not flat. So we're going to change the starting angle to pi over 3. So it's going to be at a little bit of an angle now. Everything is still its equilibrium length apart, so it's not bouncing in and out. But once it hits the surface, we're going to see these things hit the surface one at a time. Awesome. Let's watch that again. I'm going to make the window bigger this time. There we go. That's a little bit more interesting. So what you'll see here is that basically each atom is going to have its downward velocity canceled one at a time. You notice it ends up with a little bit of a bounce to it. It ends up, bouncing in and out just a little bit. That's because as it falls down, those equilibrium lengths get disturbed, and so the thing is bouncing back and forth. So this thing is behaving a bit more like a slinky per se than a rope. The damping force is taking care of that pretty soon. So if I wanted to decrease that that bounciness at the end, I could increase the damping coefficient or increase the spring stiffness. I don't think it's going to make too big a difference right now. Let's put this back to pi over 2. And what I want to do now is I want to show you what happens when only part of the rope hits a surface. So what I've got next, we're going to keep the surface at the bottom so that way it doesn't fall forever, but it does have something to catch it. So we're performing with a net here. A space net, not Annette. She hasn't agreed to be on the show yet. I'm just kidding. I don't know Annette. Let's see here. Here we've got a smaller surface, and it is located farther up and off-center just a little bit. So this thing is going to be over to the right and a little bit farther up than the bottom than the net that's catching it. Let's make this big again. I need to go ahead and change the size of the window, I suppose. So what's going to happen is that the rope is only going to get caught partially by this thing, so part of it falls down this way. And you can see I'm getting a little bit of a problem there because it's dragging it more than it really should be, and that maybe that was the one that was being problematic. Did I forget which one was being problematic? Let's try the other one. This other one is over to the left. And so when this one falls, this one's over toward the center a little bit more. Let's see if we get the same behavior on this one. Okay, this was actually the okay one. Yeah. Okay, so I need to actually move this comment here. Excuse me. Sorry, I got myself confused before the show started. So let's increase the size of this thing. So what you're going to see happen is, I guess better to look at it from underneath. What you're going to see happen is that part of the rope is able to fall off. The rest of it gets dragged along by that spring force. And that actually causes a delay in the rest of the rope falling because it has to pull the rest. This part is still up here, and so these are being pulled upward by that spring force. Let's see, let's get another angle on this. Let's see here. Here we go. This ought to be cool watching it from the side. You can even get a little bit more above. So you can see these continue to fall. These stay up. You can see the spring in between them stretching just a little bit, and it's pulling the rest off of it. It actually, does it turn around on itself there? No, it doesn't turn around. Okay. Yeah, no, it just goes like this, and then this part stays farther up. Cool. So yeah, so the, let's see. So the issue that I'm having now, and that I need to work on between now and the next episode, or over the course of the next few episodes, is I'm not entirely sure what's making this one behave differently. But what you'll notice, in fact, I'll zoom in on it. What you'll notice is that this spring gets stretched out way too much, and the thing ends up stretching. And once it stretches, the thing, the entire rope starts bouncing back and forth. One thing we might try is increasing the stiffness, right? So a rope really doesn't have that much stretch to it, right? Even a bungee cord is not going to behave like that. So let's see what happens if we make this thing, let's go all the way up to 250, say. So all we're doing is making the bond between the atoms stronger. Let's see what happens here. Yeah, it's still giving me that issue, and I'm not sure if that's because I'm catching it like right at the edge of one of the springs, or I'm not sure what is happening there. So I'm going to play around with that one a little bit more to try to get it fixed. What I was ultimately hoping to be able to do, what I'm going to continue working on, is having all three of those surfaces in there so that the rope has to fall between these two surfaces right here. Let's go ahead and resize this. There we go. So what you'll get now is this piece is going to fall in the middle and the rest is going to get dragged. This is what I was originally trying to do. Yeah, this part, that right side still behaves a little bit badly, the left part, and then it infects the left side, and then the whole thing becomes a tangled mess. So you can imagine this is what happens when you malign when you twist your slinky out of alignment. But yeah, I'm not entirely sure why that surface is so poorly behaved, but this surface is so nicely behaved, or I say the spring is so nicely behaved with this surface. So I'm going to do a little bit more looking into that. Yeah, I mean, it's just falling nicely. Oh, it does turn around. I was wrong. So it does flip around, which is pretty cool because if you watch it, actually, I can even show this a little bit more explicitly. Let's take atom list of in atoms dot color equals color dot green, and let's make it a little bit. Well, no, I should be able to see it if it's green. No, I certainly cannot. Oops. Well, anyway, watch the left edge right here. Watch the left edge of the rope. You notice it gets dragged. This edge flips around this way, and this edge now on the right. So the thing has flipped around like this, which is pretty cool, I think. So another fun thing to do might be, put this thing at an angle in the Z direction and then watch it, slide off. Although, I mean, essentially the behavior is going to be the same. So This has been pretty cool. I've enjoyed working with the surfaces. I need to get in a little bit more closely and see what's going wrong with the one on the right there. Maybe it's just, you know, getting caught at a bad position between two atoms. I'm not sure what's going on there. What I would like to do now is kind of put the surfaces on the back burner, because you don't really see that a whole lot in too many games. I'd also like to add in some friction that might actually solve the problem. But the next thing I'd like to do for next week's video is start working on some sort of rudimentary cut the rope style game, where you have your string of atoms, and then maybe you click on one of them and it cuts the rope into two pieces at that point, and then the rest is free to fall. And we can make, you know, some rudimentary rope-based games using that setup. So I'm going to have to bring in my recently developed skills of a graphical user interface from my FTL code, where you're clicking around inside the screen to make things happen inside the environment. So that's what I'm going to look at next time, while I work on the surface problem in the background off camera. So thank you so much for watching. I will see you next time. Bye-bye.